facto, I have again two types of induced EMF. The first type is simply called induced EMF. It's because of the change in the B field itself. The second is because of the border, the movement of the border. Okay, let me give you an example. Suppose I have an area original like this. Okay, original like this, and there is a magnetic field flowing out, right? And let's say the B field doesn't change. Okay, let's say the B field doesn't change, but I move that area. So let's say this is made of a metal wire. Okay, I'm going to stretch the wire so that it becomes bigger. So the next moment, the wire becomes that big. Okay, that of course causes the flux through that area to change because the area is now bigger. What happens to the flux, to the magnetic flux? Does it increase or decrease? Well, it obviously increased. Okay, it obviously increased, and as a result, you're going to see an induced current in that wire. Can you tell me the direction of that induced current? Well, again, the purpose of the induced current is to try to cancel any change in the flux. It's try to maintain the flux. The flux is increasing, which it doesn't like, the system doesn't like. So therefore, it tries to get you a counteracting flux going in, right? And so you need a magnetic field going in, and that of course can only be true if the current flows what? Clockwise, like this. See that? Because such a current would produce a B field going in, which tends to weaken the flux. Okay, that will be an example of a motional EMF. Again, that is because it's due to the motion, the actual motion of the wire expanding outwards. Okay, let's take a closer look at motional EMF. Right? We'll take a closer look at motional EMF. Now, let me ask you this. Suppose I have a border. All right. Suppose I have a border, and then there is a magnetic field. There is a magnetic field. For the case of argument, we say the B field in this case points into the paper. Okay, vertically into the paper. Now, in the previous example, we expanded the border. Right? We moved it like that. We expanded like that. Of course, that changed the flux. Certainly increased the flux, as a matter of fact. But if this border moves vertically in and out of the paper, okay, so I take this wire, I pull it up or push it down, moving it perpendicularly to the paper, in other words, along the direction of the B field. Okay, and let me ask you, in doing so, did I change the flux? Obviously not, right? Because you're not increasing the area facing the magnetic field. You did not change the flux, so nothing will happen. Okay, nothing will happen, even though there is a motion. How do you distinguish this type of useless motion with that type that we just discussed that actually can cause an induced EMF? How do you distinguish these two? Well, the way we look at it is to see whether or not the border of this area is actually cutting the magnetic field lines. Okay, the keyword here is cutting. You have to cut it. You see, if you go up and down parallel to the B field, you're just scraping by the B field lines. Are you cutting the B field lines? No, you're not. If you don't cut the B field lines, nothing happens. You have to cut the magnetic field lines. Okay, this is the only way to generate a motional EMF. Okay, with that in mind, now let's take a look at a simple geometry where you have, say, a uniform B field pointing into the paper. Okay, pointing into the paper, and it's a simple geometry, meaning we just have a bar. Okay, just have a straight bar of a certain length L. Okay, and it's made of conducting material. Let's assume it's made of conducting material. Okay, what I want to do is I want to see what happens if I grab this bar and I force it to move at a certain speed perpendicular to the B field. In other words, along somewhere within this piece of paper, perpendicular to the B field. So obviously I am cutting the B field lines, right? There's no question about that. How does that generate an EMF? And if it does generate an EMF, which side of this bar will now have a higher potential than the other? Because when you generate an EMF, this thing will act like a battery, right? Will act like a battery, and the battery of course has a positive terminal and a negative terminal. So what I want to know is which side is positive and which side is negative. Okay, so let's see how we can accomplish that? Actually, there are two ways to look at this problem. Okay, there are two ways to look at this problem. One is I'm going to follow Faraday's law directly, assuming there is an invisible virtual section of this complete loop. See, this bar itself doesn't complete the whole loop. I need to complete it with other segments. These segments are made of vacuum. There's nothing on it. Okay, it doesn't. Faraday's law never said the border has to be actually made of metal. It doesn't say that. So only this segment of the area is actually made by metal, and this is the segment that actually moves. The other three are assumed to be fixed. All right, they're assumed to be fixed. We can calculate as this bar moves, thereby increasing the area. We can calculate the change in flux. Okay, we can change rate of change of magnetic flux. From Faraday's law, we will be able to find the EMF, and we can even determine which side has a higher potential. It's the positive terminal. Let's see how we do that. Okay, remember, these three sides are assumed to be fixed. This bar is the only side of the area that moves. Now, given the time dt, the bar has moved from here to there, and the distance it moved is, of course, vdt, right? Vdt. And what is the result of that? That means the area has increased by how much? By length of the bar times the movement, times the displacement. So it's L V dt, right? You have increased the area of the bar of this area by that much over time dt, and this new area L V dt is also populated by the same exact magnetic field B. So if we take B times that, what do you get? You will get the increase in magnetic flux, right, over this time variant area. So this really is just d phi b, isn't it? D phi b. Okay, now given that, I want to know what is the EMF generated as the bar cuts through the magnetic field lines. Well, epsilon, isn't that equal to d phi b dt? Okay, I'm not going to worry about the magnetic, the negative sign for now. I'm going to just take an absolute value. Okay, I'm just going to take an absolute value for now. And what is that equal to? Move that dt down here. Isn't that equal to B L V? See, this is an important formula for the simple case where you have a segment of the border moving, and that segment has a length L exposed to a uniform magnetic field B, and it's cutting through the B field lines perpendicularly. Okay, it has to be perpendicular. In other words, the motion has to be perpendicular to the magnetic field, perpendicular with a speed v. Okay, you will generate an EMF on the bar which is equal to B times L times V. Now, the product of three quantities makes sense. A greater B field, a longer bar, and faster cutting, of course, will mean that you have greater or faster change of magnetic flux over time, and therefore you will generate a greater EMF. Okay, so this is one way to look at it. But you may say, well, this is just Faraday's law. How do you know Faraday's law is right? Of course, Faraday's law comes from countless experiments, but there is an alternative way for us to look at what's actually going on in the bar without simply just resorting everything to Faraday's law. We can look at what's going on in the bar. If it's a metal bar, we can have movements of free electrons. They can actually move up and down if there's an electric force on them, right? We can actually see what happens. A real metal bar. In a real metal bar, we have those negative charges, freely moving electrons. Let's focus on one of them. Okay, let's focus on one of them. You take that bar and you move it in that direction. As a result, this electron would then be moving that way, right? Now, as the electron moves that way, remember, it's a charged particle in motion in the magnetic field. What's going to happen to that electron? Well, it will be subject to a magnetic force, right? It will be subject to a magnetic force. Do we know the direction of that magnetic force? Well, direction is, you look at Q V cross P. Okay, that is the force formula. Q V cross P. V is like this. This is V. Okay, B is into the paper in our case. So V cross B, okay? V cross B is up, right? Is up. But remember, Q for electron is negative, so the actual direction of the force is downwards. That means electrons will receive a force going downwards, okay? As a result, they're going to accumulate here. You get a whole bunch of electrons here. And there will be a deficiency of electrons at the other tip, so that end will be positively charged. Okay, will be positively charged. So, what does that tell you? It tells you which side has higher potential, which side has low potential. You know that much, right? Okay. Also, can you find the EMF, the potential difference between these two ends? So you think of it as a temporary battery, okay? The EMF is not due to any chemical energy or whatever stored in the battery. Rather, it's because Faraday's law of induction, I'm moving it, I'm forcing it to move, cutting the magnetic field lines, therefore generating a temporary EMF as long as I keep on cutting the field lines. Okay, so what is the EMF? Well, suppose I can find the electric field produced by what? By the accumulation of positive charges here and negative charge here. Suppose there's an electric field from here to there. You know the electric field points this way, right? Because it's got positive charge, negative charge. And therefore the electric force on a negatively charged electron should point upwards, and that should cancel with the magnetic force pulling it down if the movement electrons have stopped this way, so that eventually you reach the dynamic balance, so that each electron receives the same amount of magnetic force going down and electric force going up, right? So that they are no longer migrating down here, rather they will just stay where they are and simply be moving that way. Okay, you know the magnetic force exerted on this electron in terms of magnitude would be E times V, the speed of the electron, times B, right? And that's going downwards, right? That's going downwards. That's why you get a whole bunch of negative charges accumulated here. But the counteracting electric field, electric force, is upwards, and that will equal to E times the electric field. It's an electric field in this direction, actually in the electric force in this direction, or the electric field opposite in that direction, caused by an accumulation of negatively charged electrons and positively charged ions there. Okay, and when the forces are balanced, these electrons will no longer migrate downwards. Okay, enough of them already here, they will just keep on moving this way. This tells us the resulting electric field internally within this bar, right? And it is equal to what? It is equal to VB. Sort of like the velocity selector thing, right? You got a balance of electric magnetic force, and this is the resulting electric field. Now, once you have the electric field, what is the potential difference between this end and that end? Well, we know how to do that, right? If it's a uniform electric field, the potential difference along the field direction will be E times what? D. D being the separation between 2 points. Here, you go all the way between one end and the next end, you get L. The length is L. So therefore, you find that the potential difference between the two ends, which of course is the EMF, equals what? E times L. Right? E times L. Now, wait a second. E is VB. So isn't that V times B times L, or B, L, V? See? The same thing as that. Okay, so there is really no mystery when it comes to the motional EMF. The Faraday's law of induction doesn't come from absolutely nowhere. Rather, it is totally in agreement with what happens to these moving electrons, mobile electrons in a piece of metal. As I take that metallic bar and I cut through magnetic field lines with a speed V. Okay, these electrons will achieve a dynamic balance. In the beginning, some of the electrons will migrate downwards, and then when enough electrons are there, they will establish an electric field which is strong enough to stop more electrons from going downwards. So eventually you reach a balance between E force and B force, and from that you can find the internal electric field, which gives you the EMF, the potential difference between two ends. So really it's just a matter of balancing electromagnetic forces. Okay, so naturally this side will be positively charged, that side is going to be negatively charged. Now, which side has a higher potential now? Obviously this side, right? Because it's got positive charge, that side is negative charge. What kind of current would it be deriving if I had one complete loop. See, this thing is just a battery, okay? It acts like a battery. In order to drive a real current, I must also have an actual loop going around between the positive and negative terminals of the battery. Since this is the positive end, that is negative end. If you imagine there is a Y here, Y here, Y here, connecting the positive and negative terminal, then a current will be flowing from the positive to the negative, so the current in this case will be flowing counterclockwise, right? Like that. If you had a metal wire, metal wire, metal wire. Does that make sense? Does that agree with the prediction of Faraday's law? Well, what does Faraday's law say? Faraday's law says that nature does not want to change the magnetic flux. Okay, so if you look at the flux in this region, it's downwards, right? The magnetic field is downwards. And as you increase the area by moving this bar, the downward flux increases because you get greater area, okay, in which the flux goes downwards. So the downward flux increases over time because of the enlarged area. Nature doesn't like that. Nature doesn't want the downward flux to increase, and the only way for nature to counteract that is by creating an upward flux, okay? An upward flux. An upward flux means that the current in the loop has to be counterclockwise, because that is how you create an upward flux. See that? Upward flux. If the current goes clockwise, you would be getting an inward flux, but that is counterproductive because you don't want the inward flux to increase. It's already increasing, right? You want to stop it from increasing. So either way, okay, either by using the Faraday's law directly or by figuring out how these the electrons are balanced in electric magnetic force, you get the same result. And the result is by forcing this metal bar to move in the magnetic field, cutting field lines, you will generate a potential difference between the two ends of the bar. The bar is now acting like a battery. And how much is the potential difference? It is B times L times V.